Hi, welcome to our NIPS paper on hunt for the unique, stable, sparse and fast feature learning on graphs. In this paper, we present new ways of extracting feature vector for graphs. One of the very interesting problems in learning on graph is solving graph classification problem. Basically, we would like to predict the class label associated with the graph. It has wide applications from molecular classification in bioinformatics to identifying user-choice circles and also in recommendation system. There are many ways of converting a graph into a feature vector. We believe that the graph important features are encoded in the multiset of all node pairwise distances. Taking the histogram of this multiset will give us the graph feature vector. We'll show that this idea is conceptually simple but also powerful enough to capture the substructures of a graph. Our idea hinges on choosing an appropriate distance metric on the graph. For this purpose, we discovered a family of distance called graph spectral distances based on the spectral properties of a graph Laplacian. As shown in the figure here, spectral distance between any two graph node x and y is calculated based on the weighted sum of the difference in eigenvector values, and further this weight itself is a function of the Laplacian eigenvalues. So the question is, what's so special about this family of distances? Depending upon f lambda function, one can capture different type of information about graph substructures. For example, polynomial function of f lambda captures local substructures, while the inverse polynomial function captures global structure information as shown here. Several known graph distances can also be derived from the family of graph spectral distances. The main aim of this paper is to find the best f lambda function that can exhibit ideal graph feature properties like uniqueness, invariance, stability, sparsity, and can also be computed in fast manner. During this hunt, we found out that the graph spectral distance metric is unique and its multiset is invariant under the permutation of graph labels. We also found out that its elements are more stable for decreasing function of f lambda. Lastly, we conjecture that putting f lambda equals to 1 by lambda produces the most sparse feature vector. Finally, we show that our graph feature vector can be computed exactly in O(n) squared time in worst case, and while can be approximated in O of number of edges in the graph. Here, we show our classification results on social network datasets against several state-of-the-art algorithms including graph convolution neural networks, graph kernels, and other graph spectrum. As we can see, for some of the datasets we gain significant increase in the accuracy and set the current state-of-the-art. Similarly, in bioinformatics, we see significant gain in accuracy for several datasets. Although not shown here, in terms of speed, the method is also 2 to 10 times faster than the existing ones. Thank you all for listening. See you at NIPS conference.
Created using Powtoon.